Hello and welcome back to the Quantum Information Reading Seminar, where our goal is to read and understand the paper Black Holes as Mirrors by Hayden and Preskill. If you recall, in the last episode we left off having discussed thermalization times of black holes, and that in particular we assess the timescales associated with the thermalization of infalling information into a black hole. In today's video, our goal is to read through the section Efficiency, which now gives a rather more fine-grained description of the dynamics or the assumed dynamics of a quantum dynamics of a black hole. And I will proceed to read through the section and offer comments and interpretation as we go along. Efficiency. In section 3, our analysis of the quantum model of a black hole was, as a computer scientist might put it derisively, merely information theoretic. We in effect assumed without justification that the unitary transformation arising from the internal dynamics of an n-qubit black hole is typical with respect to the Haar measure on U2 to the n, and we also ignored the complexity of Bob's decoding algorithm. So if you recall, the dynamics of the black hole was assumed distributed according to some Haar random unitary, and Bob was given in this discussion sort of infinite processing power, whereby when he collects all the outgoing radiation from the black hole, he's allowed and able and assumed to be capable of performing any unitary operation within the allowed within the laws of quantum mechanics. However, what's happening here in this section is that the authors are now going to engage with the problem that even though something may be in principle possible, such as an arbitrary unitary transformation, it's in principle possible to perform any unitary transformation within quantum mechanics, that in practice there are complexity limitations. You know, it takes a long time to actually implement certain unitary operations. They continue with, the vague picture offered in section 4 depicting thermalization as the rapid spreading of a droplet does not by itself provide much support for describing a black hole's dynamics as a random unitary transformation. Can we defend this assumption? In accord with the black hole complementarity hypothesis, let us suppose that the internal dynamics of the black hole is governed by a strongly mixing local Hamiltonian acting on n qubits that are distributed uniformly over the black hole's stretched horizon. The relevant keywords here are strongly mixing local Hamiltonian and n qubits that are uniformly distributed over the black hole stretched horizon. Here n, up to the factor 1/4 log to the base 2 of e, is the area of the horizon in Planck units, and the Schwarzschild radius is Rs's order root n in Planck units. Though we don't understand quantum gravity well enough to analyze the internal dynamics in detail, we might nevertheless hope to make a few cogent general observations. Now, a side remark on the terminology strongly mixing local Hamiltonian. I don't believe this is, even to the current time, a well-defined concept, as in mathematically rigorous. The words strongly mixing and local and Hamiltonian, they exist in a little bit in tension with each other. So firstly, you know, a local Hamiltonian, what is that? Well, that's something which is a sum of local interactions. Here we don't mean spatially local, we just mean that the number of particles involved in each interaction is, say, small, or say two-body. So here's an example. A two-body local Hamiltonian H would be the sum of a bunch of coefficients, and would have this particular form here. So the sigma alpha notation stands for this vector of Pauli operators. So we're talking about qubits here. Oops, I forgot the x operator. 0, 1, 1, 0, 0 minus I, and 1, 0, 0 minus 1. So these are the four Pauli operators, including the identity. We can express any two-body local Hamiltonian as a sum of tensor products of Pauli operators with some coefficients h, j, k, alpha, beta. Now, that's what local Hamiltonian might mean in this context, or local two-body Hamiltonian. You can imagine what three-body and four-body means, etc. What is strong? So that's what local means. But what does strongly mixing mean? Well, you have to be a bit careful, right? Because if we assume that the dynamics of the system is unitary, and this is a key point in this section, right? So if the system, the black hole or whatever, evolves unitarily according to this Hamiltonian, then the propagator for the system is ut is e to the minus ith in units where h bar is 1. And that's a unitary, right? And so what could it mean, strongly mixing? Mixing is terminology that comes from the study of Markov chain stochastic processes. You might think that things get less distinguishable as time passes. However, that's impossible, right, under unitary dynamics. If two states, phi and psi, are orthogonal, if the inner product between phi and psi is really exactly 0, then no matter how you evolve these states in time, they will never become distinguishable. They will never ever, the inner product will never ever stop vanishing, will never ever go above 0. And that's just unitarity. That's what unitarity, that's a direct consequence of unitarity, and the fact that inner products are preserved by unitary linear maps, by unitary maps. This inner product remains 0 for all time. These two states never become less distinguishable. They always remain 100% distinguishable. So the word mixing here, although it semantically implies somehow that the dynamics makes two states somehow get less distinguishable, that's not what happens on the unitary dynamics. However, there is a sense in which unitary dynamics can lead to things becoming less distinguishable, and that's a key point, and that's going to be exploited in this section, and there's also an extraordinarily important point in the study of many-body physics. So this result that I've just drawn here, that the inner product is always 0 under unitary dynamics if it starts at t equals 0 at 0, that's only, this means, what's the physical meaning of this? There exists, in principle, a measurement which perfectly distinguishes phi t and psi t. The thing is, though, this perfect measurement, the one that does that distinguishing, is extremely non-local in general. Even if at time t equals 0, the two states are easy to distinguish with some sort of local observable, as time passes under the unitary dynamics of a local Hamiltonian, these two states become more and more entangled amongst all the subsystems, and it becomes less and less easy to distinguish them locally, although you can always distinguish them globally. So if you add a certain constraint, a physics-based constraint, that measurements must be also be local. So if you demand that the measurements that you're allowed to perform must be themselves local, then phi and psi can become less distinguishable. And now we really can talk about the notion of mixing, or strongly mixing. And so then what would mixing mean in this context when you're not allowed to apply an arbitrary measurement operation? So this is the key extra constraint that gives the physics here some life. Well, mixing means that these states, phi t and psi t, become, let's say, locally entangled, or maybe the better way to say that is that the local degrees of freedom of phi and become entangled with each other. And how do you witness this? How do you see this? Well, look at the reduced density operator. For say a single spin. So, let's just focus on spin 1, for example, from the state. That's what you get when you trace out everything except the first spin of the state phi t. Now, generically, it's a fact, experimentally observed, let's say, numerically experimentally observed fact, that these states rho 1 of t, as time passes, they rapidly converge to the completely mixed state. This is just something that you generically observe when you numerically solve these systems. There exist systems where you can prove that phenomenon, but you cannot prove that this happens for all time. Why not? Well, there are things called Poincare recurrences. There exists a time, doubly exponentially far away, when the state phi of t under the unitary dynamics generated by the local Hamiltonian will come arbitrarily close back to itself. So although you can look at these local reduced density operators under the dynamics of a local Hamiltonian and see that the distance between some local reduced density operator and the completely mixed state, you can plot that versus time, and you see something really remarkable, right? Maybe at time t equals 0, they're extremely far from being a completely mixed state. So, the trace distance is basically 1, and then as time passes, they rapidly become indistinguishable. And then you sort of see this behavior. The distinguishability wiggles around like this under the dynamics of this local Hamiltonian, and then doubly exponentially far in the future, or triply exponentially, doubly exponentially far in the future, there will exist a Poincare recurrence, and where they will become distinguishable again. So this is the best way to interpret the words mixing in the context of unitary dynamics. Globally, unitary dynamics do not mix anything. However, locally, things can become less distinguishable because the local constituent degrees of freedom become entangled with the other ones, and when something becomes entangled with another degree of freedom, then it becomes mixed. The local degree of freedom becomes mixed, and when it reaches maximal entanglement with other degrees of freedom, it's maximally mixed, and that state is less distinguishable from another state that's also locally maximally distinguishable. So that's just a parenthetic remark on what strongly mixing local Hamiltonian can mean in this particular context. We find it helpful to envisage this dynamics as a local quantum circuit where in each unit of time, 2-qubit unitary transformations, quantum gates, are applied in parallel to about n over 2 pairs of neighboring qubits. Okay, why is that justified? Well, that's just, why is e to the minus, why can we just sort of conveniently throw away this solution to the Schrödinger equation and replace it with a quantum circuit? Well, that's actually a not particularly difficult consequence of the fact that there's this thing called the Lee-Trotter formula. The idea is you break up the Hamiltonian into collections of pairwise commuting terms. So we call them like A plus A1 plus A2 plus whatever n, and each 2-qubit term here pairwise commutes with each other term in AJ. So that's the decomposition. So if you have a Hamiltonian where the interactions are arranged on a one-dimensional line, you can actually get away with just two groups here. However, when you've got this sort of complete graph every qubit talks to each other qubit. Then you have to decompose your Hamiltonian into a larger collection of such internally commuting terms. And then the Lee-Trotter formula tells you that that is approximately equal to the product of the exponentials separately of these terms, divided by, let's say, capital N. Oops. All to the power of capital N. So that's what Lee-Trotter formula tells us. And then you can look at these terms and realize that, indeed, they are, because everything pairwise commutes inside the term A, these terms themselves break up into products of now 2-qubit unitaries. You get all these sort of local terms where these interaction pairs come from some set Sj of interactions associated with edges which don't touch. So I'll draw a quick graph example. So if you have 4 qubits, for example, and you've got an interaction between each edge, then here's what the interaction graph might look like. Every pair of qubits can interact. And what are the edges associated to each of these A operators? Well, I can color them, different colors. So we might define A1 to contain those interactions that only touch qubits 1, 2, and 3, 4. 1, 2, 3, 4. And those might be the interactions involved in those edges. We might call associate to the operator A1. And then the operator A2 might have the qubits associated to the blue lines, and the operator A3 may be associated to the green lines. And so that's how you can decompose the dynamics of any local Hamiltonian, low body, few body Hamiltonian, into the sum of terms which themselves contain only pairwise commuting terms. And then if you look at this object here, this product of exponentials of 2-qubit terms, you realize that indeed this is just a product of, I forgot to name this. Yellow is the set S1, blue is the set S2, and green is the set of edges S3 in this particular example. Then you see that this is really just a product of unitary operators associated with these different sets, and therefore parallel applications of 2-qubit unitary operators. It seems natural to choose the unit of time to be the Planck time, but according to whose clock? This is a subtle question because due to gravitational redshift, the clocks of static observers hovering above the stretched horizon run much slower, by a factor of the order Rs in Planck units, than the clocks of observers residing far from the horizon. As already noted in section 4, there are physical processes on the stretched horizon, like the distribution of electric charge, that can act over a proper distance of order Rs and Schwarzschild time of order Rs. If we wish to accommodate such processes in our circuit model, we may take the unit of time to be the Planck unit of Schwarzschild time. This model of the local dynamics on the stretched horizon is very naive, and in particular the model does not attempt to address the challenge of reconciling rapid spreading of information with causality. In any case, and that's important because an epsilon of time later, information is spread all over the stretched horizon. So it's causally questionable. In any case, no matter how we prefer to map circuit time to physical time, it is useful to characterize the circuit complexity of global thermalization. In our model, after a Schwarzschild time t, the unitary transformation acting on the black hole's internal state is realized by a circuit that has a number of steps, the circuit's depth, of order t, where t is expressed in Planck units. This is an assumption about the dynamics. And the assumption is motivated and justified by these observations here about local Hamiltonians and the dynamics of local Hamiltonians. And the total number of local quantum gates, the circuit size, is order nt. And you can see that n comes from the number of partitions of the Hamiltonian into these terms A1, A2, A3, all the way up to AN. And t is the time t that we run for. Now, unfortunately, if T is polynomial in N, then Haar random unitary transformations cannot be generated by circuits of this size. And this is a really important point. This is essentially just a counting argument, and perhaps a little bit surprising. So the claim is Haar random unitaries cannot be generated by local Hamiltonians for T, which is order somehow poly in the number of qubits. Now, why would that be true? Well, a simple counting, absolutely simple naive counting argument already gives you a hint that this might be the case. So the number of parameters to specify a local Hamiltonian, how many are there? Well, you know, there's n choose 2 pairs of qubits, and per pair of qubits you need something like 16 numbers. So, you know, that's roughly speaking order n squared. That's the number of parameters required to specify a local Hamiltonian acting on n qubits. Now, if you had a 3-body, this of course was applying for a 2-body Hamiltonian. If you had a 3-body Hamiltonian, then the argument is practically the same, right? You know, some constant, and you know, this is order n cubed, which is good enough for government work. Approximation to the number of parameters required to specify a 3-body Hamiltonian, and so on and so forth. But the key point is there's a polynomial number of parameters required to specify the Hamiltonian for a few-body Hamiltonian. How about how about just a unitary? How many parameters do we need to specify a unitary U in the unitary group acting on on n qubits? Well, that's a unitary in the unitary group U to the 2 to the n. So, roughly speaking, you need 2 to the n by 2 to the n complex numbers, right? But you don't need quite that many because there's a couple of equations that unitarity implies that U dagger U equals the identity, and that gives us, you know, 2 to the n. It gives us roughly 2 to the n by 2 to the n equations. So you're left with, you know, roughly speaking, order 2 to the n numbers required to specify a unitary U. I mean, you can make that more precise. It's really 2 to the n minus 1, but whatever. It's good enough as an order of magnitude estimate. And then you can sort of already look at it and say, ooh, that doesn't look good, right? We've got somehow n squared versus 2 to the n parameters. And so already you get a sense that the number of parameters to specify a completely random unitary is vastly outnumbers the number of parameters you have at your disposal to specify a local Hamiltonian. So, you know, it's probably not the case that you can specify a unitary a generic random unitary U probably can't be written as e to the ith for some few body Hamiltonian and some small t. However, the question is very fascinatingly more deep and interesting than this naive counting argument would suggest. So the first point is that although you can't write U perhaps potentially as the exponential of a few body Hamiltonian, then there presumably does exist moments in time when this unitary generated by the dynamics of the local Hamiltonian come arbitrarily close to a specific unitary, random unitary. And so you might be thinking, well, you know, maybe it's not so trivial. And in fact, it isn't trivial, and to do the counting argument properly requires a much more fine-grained approach to the geometry of the unitary group. And this argument's been, you know, made and formalized, and I'll just point you to a particular reference here where they've carefully gone through the dimensions and counting arguments required to prove that truly, indeed, it is impossible to approximate an arbitrary Haar measure distributed unitary with a local few-body Hamiltonian for short times. So this is indeed true. And here the authors give some sense of this argument. In fact, because the volume of U2 to the n is exponentially large and to the n, reaching a typical unitary transformation requires a size whose circuit is exponential in n. Okay, to fully expand that point, you really should read through the reference I just gave. However, much smaller circuits can be good encoders for quantum error correcting codes. In particular, the capacity of the quantum erasure channel is achieved by typical stabilizer codes, and these are super simple codes generated by commuting operators, which have encoding circuits of size order n squared. Furthermore, good approximate encoding circuits can be even smaller. If we replace the integral over all unitary transformations by an average over elements of an epsilon unitary 2 design constructed in 6, then equation 6 is modified to become this. Each element of k can be realized by a quantum circuit that has size n log 1 over epsilon and depth order log n log 1 divided by epsilon. It seems reasonable to expect that random quantum circuits built from 2 qubit gates would encode at least as efficiently as the approximate 2 designs that have been explicitly constructed, and preliminary results from numerical experiments are consistent with this expectation. So we could take a deep dive now into epsilon approximate unitary 2 designs. However, I'm going to resist that temptation because that really would be the subject for yet a complete other seminar, and rather simply point you to a paper where these expectations that random quantum circuits, or in particular the dynamics from random local Hamiltonians, are shown to at least approximate the required inequality and the main inequality of this paper. So I'll point you to a paper where this is discussed, and it's the one that actually brought me into the subject. So the paper where we studied the dynamics of local Hamiltonians and asked the question, although a local Hamiltonian can never get you close to an arbitrary hard distributed random unitary in a short time, perhaps it brings you locally close enough, or close enough in correlation that the main inequality of the black holes as mirrors paper would remain true. And this paper here is one that I did together with Patrick Hayden, amongst others. And in this paper, we study a variety of different dynamical models for black hole dynamics, and studied how close and how quickly these random circuits so-called scramble or become mixing. So this is really a sort of jumping off point for yet again. Could easily spend a whole other seminar on talking about the details of this. We won't. I'll just place the link here and you can follow it up at your leisure. The summary is, and the key point is, to draw from all of this discussion, is that although e to the minus ith cannot approximate a hard distributed random unitary, the key point is this doesn't matter. Because really, we don't want a hard distributed unitary. All we want is that the main inequality of the paper is true, and that's a far weaker requirement on a unitary operator. So the main inequality of the paper is, let's say, equation 6, and equation 6 can be proved assuming that the dynamics of a black hole is hard distributed, but it also turns out that equation 6 can also be proved for a far weaker class of unitaries, or at least that's logically open at this stage in the paper. In fact, this has really launched many ships, this observation, and in fact there's been an extraordinary amount of follow-up work studying dynamics according to various different local models, and checking whether or not indeed equation 6 is true or some variant thereof. So this is a really fantastic moment fantastic jumping off point to a vast body of really fascinating and interesting literature. For the purposes of this paper, however, we are happy just to conclude that the dynamics of a black hole, the internal dynamics of a black hole, does not need to be coming from a unitary distributed according to half measure, but can in fact arise from local unitary dynamics generated by a few body Hamiltonian. It seems reasonable to expect that quantum random circuits built from 2-qubit gates would encode at least as efficiently as the approximate 2 designs that have been explicitly constructed, and so we have read that. And that is now a true statement. I'm not quite aware of the state of the art here, but these results have definitely been investigated in the intervening years and are 100% justified and confirmed. This estimate of the circuit size and depth does not take into account any geometric locality constraints, right? I assume that every qubit interacts with every qubit. If the n qubits are uniformly distributed on a 2-dimensional sphere with radius order root n, then the additional cost of using local gates should be at worst to blow up in size depth by a factor of order root n. Since the information stored in a qubit can propagate a distance root n when root n local gates are applied in succession. Right? It takes time for information to propagate around a sphere. The propagation time is bounded by something called the Lieb-Robinson bound. That's explained in the paper I cited above. I just mentioned this terminology here if you want to follow up this line of investigation. I'm not 100% clear myself on what the state of the art is for degrees of freedom distributed on a sphere. It could be that there's some constants and factors to be won still in these discussions. But at this point here in this paper, you should regard this as sort of plausible conjectures. But my claim is that in the intervening time, people have investigated these plausible conjectures and actually justified them rigorously. But here, at the level of plausible argumentation, we can certainly conclude that there exists a good approximate local encoding circuits for the quantum erasure channel that have size n to the 3/2 log 1 over epsilon and depth n to the 1/2 log n log 1 over epsilon. And the expectation here of the authors is that the random local circuits of this size and depth would do at least as well. Therefore, if we model the internal dynamics of the stretched horizon by a random local quantum circuit, we conclude that the global thermalization of the black hole is achieved by a circuit whose depth is order Rs log 1 over epsilon. By global thermalization, we mean that such that equation 8 holds, so that Bob can approximately decode Alice's quantum memory with a loss of fidelity of order epsilon. Now, I think, personally speaking, I think global thermalization is a slightly misleading word, terminology, given that that unitary circuits can never lead to mixing globally. So the word global here is a little bit hazy. So we'll just, perhaps we should say something like effective thermalization, effective global thermalization. I feel like there's an adjective that could be added here to tighten it up a bit. Modeling the internal dynamics of a physical system by a small random quantum circuit is far more defensible than modeling it by a unitary chosen with respect to half measure, because a small circuit can be realized by physically plausible local dynamics. It therefore seems reasonable to suggest that the dynamics of a black hole could efficiently generate good quantum error correcting codes for the quantum erasure channel. Indeed, if each computational step occurs in 1 Planck unit of Schwarzschild time, then the thermalization time, T, is order Rs log Rs, scales with Rs as in our crude estimate in section 4. Now, they point out the problem that's present at all stages of this discussion. Decoding, however, can be a much harder computational problem than encoding. Black hole evaporation maps Alice's k qubits to a highly non-local subsystem M prime of RE. Remember, the radiation comes out in 4 pi radians. It's going everywhere, and it's all sort of smushed up. Bob's decoding operation maps M prime back to the compact system M hat localized in his laboratory, returning the qubits to a usable form. Even if we are willing to grant Bob the power to collect all of the Hawking radiation emitted by the black hole, Bob might not be able to recover Alice's k-qubit message by means of an efficient quantum computation, right? It's the information's there, but it's buried extremely non-locally in some horribly huge entangled state. And it might be, and it probably is, that the resources needed to perform Bob's computation might grow faster than any power of k. Actually, if a stabilizer code is used to protect entanglement-assisted quantum communication through the erasure channel, then Bob's decoding operation computation is easy. Bob can replace each erased qubit by the standard state 0 and then measure the code's check operators. With high probability, there is a unique Pauli operator acting on the erased qubits that restores Bob's state to the code space, and the recovery operation can be efficiently computed using linear algebra. However, this recovery procedure exploits the special structure of stabilizer codes and would not work for typical non-stabilizer codes. If and so that I think is, so we're given, we have the hope that maybe you can always efficiently decode, because there is this example of a quantum error correcting code where you can efficiently decode, but it's probably not the case for more typical local dynamics. And why should a black hole be, have anything to do with stabilizer codes? If thermalization is rapid, then the quantum codes realized by evaporating black holes have small encoding circuits, and therefore they too are rather special. But they are not stabilizer codes, and we do not know whether they are efficiently decodable. Conceivably, decoding is hard not only for n large with k over n fixed, but for n large with k fixed. If Bob's decoding problem is intractable, then physicists of our highly advanced civilization may be hard-pressed to test the hypothesis that black holes re-radiate quantum information quickly. For that matter, one might question the testability of the claim that black holes really preserve quantum information. We emphasize, though, that even if Bob's decoding problem is hopelessly intractable, the physicists of our highly advanced civilization, using only polynomial resources, should be able to test the hypothesis that black holes process quantum information without destroying it. Once these physicists understand the laws of black hole dynamics well enough, they should be able, using their quantum computers, to simulate the formation and complete evaporation of a black hole. Through a swap test, they could compare the output of their quantum simulation with the observed product of the black hole evaporation, and therefore verify that dynamical black hole is behaving as their theory predicts. The feasibility in principle of such a test boosts our confidence that the assertion that black holes preserve information has a well-formulated operational meaning. However, and here's a note, unfortunately the swap test only works for comparing pure states, not mixed states. It can't be used to compare the simulation with experiment in the case of a partially evaporated black hole. So what's going on here? What's this swap test? Blah, blah, blah. Well, suppose you want to check if two states are the same. How might you do that? Well, let's suppose that we have the two states available for checking. So we have state phi, and for the sake of argument, let's keep this to be qubit states. We have the state phi in some register, the state psi in some register. How does a swap test work? Well, you add an ancillary qubit that you put in the state 0 plus 1 over root 2. Then you apply a conditional unitary. I'll write out the matrix elements of that. So this conditional unitary applies the swap operator if the control qubit is 1 and does the identity otherwise. And then you measure. So this is the swap test. So what is this unitary operation here? C swap, let's call it. Well, it's the following matrix, which I'll specify in block form. So it's an 8 by 8 matrix. And in bracket form, it's this operator. So why does this work? You can go ahead and work out the success probabilities, and you'll see that probability of getting 0 is related to the overlap between phi and psi, and the probability of getting a 1 is related also to, I believe it's a half plus a half, this squared, a half minus a half, this squared. Maybe it's the other way around actually. Just from memory. So So this is how you can check if two quantum states are the same, or actually to really estimate the fidelity between two quantum states. Let's suppose that the states are the same. Let's suppose that psi is exactly phi. Then let's analyze the dynamics of the swap test and just convince ourselves that it would work. So if the two states are the same, then swap acts the same as the identity. So the state that you get upon applying this controlled unitary here doesn't care about what the ancillary state is in, either 0 or 1. So in fact, the state before is the state afterwards. And you will measure with a probability exactly a half, a 0 or a 1. However, if the states are, say, completely orthogonal, then you send the two states through, they swap, and then the states become distinguishable. There's a different action depending on 0 or 1, and that affects the success probability. So now I'm slightly unsure if I've remembered this correctly. Probably a good idea just to check the example where phi and psi are 0. The inner product of phi and psi is 0. So before the whole procedure commences, the swap test commences, the initial ancillary state is in 0 plus 1 over root 2, and the rest of the system is in the states phi and psi. Then we apply this controlled swap, and the state after the controlled swap operation has now changed. And then that's stage 2. And now we measure the observable sigma z. And let's just work out the probability that we get a 0. So that would be equal to, let's give the state a name here, capital psi or something. So P0 is the probability that upon measurement of the sigma z observable, you get a 0. And that's found by computing this expectation value here. And you find that that's exactly a half, right? And P1 is also a half. So I've done something. Yeah, I made a mistake. I forgot part of the circuit. I knew there was something funny. You have to do a Hadamard gate after the whole thing has happened. Now I believe everything should work as advertised. So let's just do it as before. So I missed out that part of the circuit where we do the Hadamard gate on the ancillary qubit. So when you do the Hadamard gate, I'll just do it quickly, you get 0 plus 1 in here, phi, psi, plus, and you get 0 minus 1 over here. Psi, phi, and that's what we'll call big psi. And now we'll measure P naught. And let's hope things work out. I don't know, maybe. And what do we get? Well, we get P naught. I'm going to do this real rapidly, right? So I may make a mistake, but I believe you get a half plus, and then if you get another contribution, a potential contribution from a cross term here, but that's actually 0. And the same goes for P1, right? It has to be. Now, if the states were completely indistinguishable, however, you would get P naught is 1. Then, if we go up here, we see that we have the same state after the Hadamard operation. And actually, something that's quite remarkable, is that capital psi in that case really would just equal 0 phi phi, right, after the Hadamard operation up here, right? You take a look at the Hadamard operation here. Suppose phi equals psi, that's the same as that. Well, then you can factorize these things and you see that the one contribution cancels and you're just left with the posterior state being 0 phi phi. And so then P0 is 1 and P1 is 0 after measurement. And so that's how you see that the swap test unitary can tell if two states are the same or not. And in fact, you can further carry out this analysis and see that the success probability is related as I advertised to the fidelity here. So I guess I made a mistake, and the answer is there is indeed a plus there and a minus there. Okay, so that's oh yeah, and so how can our future future civilization test these hypotheses? Well, what they can do is they can get some lots of entangled pairs, push the entangled pairs together until they form a black hole, wait some time, capturing the radiation that comes out of the black hole, and now after the black hole is evaporated and there's nothing left, then what they have is they have their reference system that they had all along, right, is entangled with, you know, by some process, some unitary operation here with all the outgoing radiation, which they've caught, right? And then they collect together the quantum subsystem associated to the outgoing radiation, the quantum system associated to these halves of entangled pairs, and then they just do a swap operation to tell if they've captured all the entanglement, if the same state has arisen from the black hole dynamics unitary versus, so this is, so the black hole dynamics, right? You know, what radiates the degrees of freedom is, that's the experiment that they do in space-time, but they also at the same time can take these entangled pairs and send it through their model of the black hole dynamics. And so if you like, the state that comes out of the actual real black hole that they constructed, we can call that state psi. And then when the other half, right, of these entangled states, they could call phi, the one that they've sent through their model of the black hole dynamics. And then they've got effectively two copies. Okay, you really didn't need the entanglement, I realize. Okay, forget the word entanglement. I just realized that we could just tell the story slightly simpler. So what they do is they prepare a state phi of a bunch of particles, and then they prepare another state phi of a bunch of particles. Then they squish those particles together, it forms a black hole. And they've got this original state phi hanging around. Then the black hole radiates. And now they've got a state of the radiation, which is the state psi. And then they have a model of the black hole dynamics. They apply their model to that initial state, and that gives a state phi prime. And then they go, this future civilization that now in possession of all the radiation and also in possession of the simulation, quantum simulation of the black hole dynamics, can say, well, are these two states in fact the same? And to do that, they just have to do a swap test, which is polynomial in the number of particles. All right, that's, I think, a good moment to pause our discussion today. In the next and final video, I will briefly skim over the section discussing the question of whether black holes are quantum cloners. And then we will conclude the seminar for this semester. But for now, thank you very much and goodbye.